Welcome to my Commodore 64 Games Memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Nebulus, but part 2, following on from the previous video. I want to go into more detail about altering the levels, the level data compression methodology, and also the sprite flipping. In the previous video, I found where the tower draw routine was and where the platform and other game object draw routine was actually called from, and it had a common object return address, which you can see in the debugging details text file, which I use to note the details of things that I find during these deep dive technical sessions. So going back into ICU C64 and opening the memory view and also the graphics map text screens view so we can see the memory a little bit more easily. I actually had a nice little snapshot right at the beginning of the level, so it's easier to get back to rather than going back to the title screen and then coming back to the game again. So let's scroll around until we find the drawn level. From the previous video, we found that it was a double buffered text screen and the character set is there at 7800. Let's turn it into multicolor mode so we can more easily see what we're looking at. In the monitor window, I want to have a look at the CPU execution history, so I'm going to put a breakpoint at C3F6 there. And then let's have a look at, well, okay, so this one's not very good because it's got an interrupt happening during the block or the platform object draw, so this isn't a good one. Let's skip ahead to the next one. There's no interrupt running there now. So we have this routine here. Looking back through the CPU execution history, I can see at C3F1 here there is a load accumulator with an absolute address. This absolute address looks like it's within the level data memory range, and it looks like it was deciding on which draw routine to call depending on the type of the tile or object or platform that was loaded in from this memory range here. Don't forget that in the previous video, in the memory map, we could see a rather large green rectangle moving around as the player character moved around the tower. This large green rectangle shows that there's quite a large amount of memory being read, but it's not being written to, and it's not being executed from, because that has different colorization. The execution is blue and the yellow is memory write. So we know that green is memory read. And this large memory read tends to indicate that it's going to be level data. The screen updates are there in the middle of the memory view, and those are the large yellow blocks there, and also the green blocks. You'll notice as I move up and down the tower that the green rectangular block moves left and right through this memory view. Now the memory view here is organized in 256 pixels horizontally by 256 pixels vertically. 256 times 256 is 65,536, which in kilobyte terms is 64 kilobytes, because each kilobyte, KB, is 1024 bytes, especially in computer memory terminology. So this routine here seems to do with decision of, I want to load the accumulator here with a memory address which is within that memory range, from say 200 to 1200 in hex. And if it's minus, it seems to go into the block draw method. If it's positive, in other words that the high bit is not set, then it just goes over and loops around looking for more blocks. The memory address there is actually self-modified by a later part of the routine, so it modifies the memory address at C3F2 and C3F3. Just rearranging the disassembly view there and adding a register view into the window so we can more easily see what's going on, so I don't need to keep on using the CPU history command. So this early read here is at 600, which is basically the beginning of one of the tower rows. That's what it looks like. What sets this memory address? Well, this memory address is actually being set before the loop of this routine goes through and renders the platforms for the tower. So to find out where this is set, we really need to go back to where it's clearing the tower edges on the screen before the rendering loop really starts. So we'll put a breakpoint at BFCF, which was the tower edge clear routine for the screen draw. Once we're here, then we can put a watch store point at those two memory locations for where that load accumulator absolute was being used for, and that's C3F2, C3F3. We then let it run, and then we can see the CPU history, and we can see that the routine there at C381 is initializing C3F2 there. If we trace back to the CPU history, we can see that the probable entry point here is at C341. Let's see the minimum memory range, or get a good idea what the minimum memory range is here. This add with carry with 2 seems to indicate that the table, or rather the memory block for the level, seems to start at 200, because that's an add with carry with 2, but the carry is clear, and also it's storing it into C3F3, which is the high byte, the most significant byte of the absolute memory address that was being loaded just before it was deciding to draw an object or a platform around the tower. So let's have a look at the memory locations C3F2, C3F3 in the memory dump view here, and we'll run this routine a few times, and we'll see we'll get a good feel of the memory range which is being used on subsequent calls of this routine here. So if we press X and we go to the next breakpoint, we can see that it's cycling around 9 FB, 3 FB, 4 FB, 2 FB there. So we have a good idea about the range of memory that's being read during this tower object platform draw, which is very useful information. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are all always very much appreciated. With this watch store point, with this memory range, let's look for where the level data is written to. We know that we've got reads, but we're looking for memory writes. There's no memory writes going on during the level, so let's go back into the level. And here we go. We've hit a nice watch store point here with the store accumulator indirected with 06 in hex, comma Y. We can have a look at the CPU history, and we can see that there's this routine here which seems to do some repeated stores to 06 indirected, comma Y, which is useful for us to know because 6 and 7 is the memory address 300 in hex, low byte, high byte format there. So it seems to be starting a memory read, or memory write, sorry, at 300. But let's have a little bit of a closer look at this routine to see what it does, because it's not doing a straight memory copy. We can see, if we have a look at the memory being written to here, that actually there's no store going on between 2F8 and 2FF when it's inside the game. Let's go back again, and that's interesting. Even though the game is reading memory from 2F8 to 2FF, it's reading it, but there's no write to this memory range, even when it goes back out and into the level again. So what does this tell us? Well, it tells us that actually what looks like the tower platform object draw is reading some memory that is potentially not initialized at 2F8 to 2FF. And that corresponds to some of the stuff that we can see at the bottom of the tower underneath the water. Because the water masks out the bottom of the tower. The bottom of the tower seems to contain what looks like junk when it was rendering it before. I mean, the player can't get down there because it's underneath the water. So it looks like, you know, the tower draw seems to be reading a larger memory range then it's actually decompressed, which, you know, is, I guess, okay, as long as your routine doesn't crash when it draws too much. So let's go back to this routine here, which is doing stores into that memory range. And let's see if we can understand what it's doing. Well, it's doing a store accumulator indirected. It's doing a load A with 0. But look, it's doing a logical shift right there with B0, A2. And then it's doing a load accumulator, which doesn't touch the carry flag, and then it's doing a branch on carry clear. So if the shifted value of whatever is in B0, A2 is carry clear, so the logical shift right moves the lowest bit into the carry, and it moves all of the bits along to the right. So that branch on carry clear basically skips over and just stores it stores 0. But if carry is set, then it seems to be reading a value from somewhere else in memory and then storing that into the level data. That routine was doing it 8 times by looking at the loop counter, but it seems to be doing 2 calls of this same routine at JSR B0A3 there, at B083 and B086. It seems to be decompressing for each of those calls up to 8 bytes. Well, actually, it was writing 8 bytes always, but it was only reading bytes to store into the memory for the level data only occasionally. So I guess that logical shift right is some kind of like bit field. So a bit field has a bit either on or off within the 8 bits for each byte, and then it can signify whether or not it wants to store a 0 or whether it wants to store an actual platform, game tower object, or whatever it is in the level data. Stepping back out of this routine here, we seem to have a JSR to decompression, and then it runs the data. So if we go back out and come back in again, we can see that it triggers here. The memory hasn't been written to yet. This is the start of the decompression routine, by the looks of it. That's where that other breakpoint was. Let's delete all of the breakpoints. Let's go back out and try again. Oh, if you can hear rain in the background, it's because it's raining. And it's a very heavy storm here at the moment. Luckily enough, both the cats are asleep today at this particular time. It's their afternoon sleep time. So no more meowing cats at the moment. The entry point for this routine here, it seems to be looping around a good few times. Look, there's a decrement B022 branch on not equal B083. So it's B083 branches back to the start of those 2 JSRs, which each of them write 8 bytes each. So it's doing 16 byte writes in a particular pattern. Maybe this corresponds to each row in the tower, because there are 16 segments for each tower. So it reads a bit field. It's then choosing whether or not to read probably a game object or a platform type or something like that, and then optionally, and then store that red platform or game object type into the level data, otherwise it stores 0. Okay, that's a nice little decompression routine. My gut feeling tells me that actually looking at this level data, it would have been a little bit more efficient to not use a bit field method and to probably use some kind of run length encoding. But hey ho, never mind. This is decompressing each row, so it decompresses location 200 and then 300, then 400 until 1100. Then it loops back and then does 201, 202, 201, 301, 401, 501, etc., etc. I think 4A in that, looking at that routine there, is the level number, because we can test that. We tested that, right, just by putting 1 into 4A. So B043, yeah, is decompressed level with a particular level number. So this seems to be the setup for the 0-page memory locations at least at 4, 5, 6, and 7, and 0, 2, 0, 3 as well. So 2, 3, 4, 5, 6, and 7. We can see that it's reading bit fields from 2, 0, 0, 0. It's reading optional platform object types for the tower at 3018. It's intriguing that the bit field is maintained separately to the object platform types, and then the store memory address is at 200 onwards. Okay, so just documenting my thought process here. These notes will also make their way into the debugging text file notes as well. I'm thinking this, I mean, all of these values here, look like they're typical level object platform types, right? 81, 91, 83, 85. These are all values that I would see in the what looks like now decompressed level data. So after doing a little bit of experimentation with the level data that's decompressed in memory, I can modify a certain sequence of memory locations to introduce, say for example, an extra lift. So 300 in hex is the segment just to the right of where the player starts. A platform is 8.1, a lift top is 8.5, and then obviously 0 bytes are cleared bytes. There's no platform objects at those positions. Remember, each segment goes around the tower, and each of these successive bytes is actually from the bottom, moving upwards through the tower towards the top of the tower. And the bottom of the tower is level with where the water starts to get drawn for the bottom of the tower. So I noticed that a certain byte value would basically say this is the top of where the lift stops, and I noticed it was byte 8. So now when I add that string of bytes to memory, you can see that this level now has an extra tall lift right at the beginning of the level, just to the right of where the player is, that will take me up to the top of the tower, which is really quite cool. Right now I've just completed the tower just by taking the first lift that I see all the way to the top and avoiding all of the enemies and all of the block puzzles and everything like that. And there we go, the level is now complete, and we go into the bonus game again. Now of course the level data has been decompressed again. I need to add the same memory change because it's been overwritten because the level gets decompressed. I want to save this data and I want to try and compress it by writing a compression, by writing a version of the compression routine which is compatible with the decompression that's being used in the game using this bit field and optional platform or object type identification. I do need to clear this memory range first though, because the decompression is sparse and it's got a whole bunch of extra stuff floating around in the background there, which actually the game doesn't really need. So let's fill the whole memory range for the whole level data with zeros. So now we can see in the graphics text screens map that it's all nice and cleared. And then if I let the decompression routine do its thing here, so we'll continue until we get to the RTS, and then we'll hop back out of the RTS. We'll put a breakpoint here, which is after the decompression routine here. So this, we can see in the graphics map now that there's some level data there, but it doesn't contain all of the extra rubbish uninitialized data that was there previously. It's probably from the load previously or from some decompression or memory move, right? So this is the tall lift that has been put back into the memory after the decompression has been run. And then that's the level data. And the reason why I clear the memory is because I don't want all of the extra memory to be considered for compression. However, the compression is sparse. It doesn't decompress the entire memory range from 200 to 11FF in hex. It only compresses the rows which are being used for the tower. So we need to take that into consideration. I'm going to be using Python. I'm going to be taking a copy of the Paradroid data extraction Python file, and I'm going to copy it and call it Nebulus, and then I'm going to modify that because the code is a little bit similar in that it needs to read a binary file and then write binary files, so I might as well just copy and paste that and then alter this code to do the compression. So let's have a look at the Nebulus file, and let's start to alter it so it suits this new intended purpose. There we go. I'm going to fast forward through this at super speed, so you're not going to be seeing a lot of, well, you're not going to hear a lot of stuff, you're just going to see a very quick development process. One moment, please. At this point we have the compress single bit field method, or function if you like, which is called twice because don't forget that the decompression routine also decompresses the bit fields twice. It's at this point that I realize that I need the original data. If I want to compare my compressed output with what is actually in the game's memory, I need to have an unmodified Nebulus level 1 rather than Nebulus level 1 with my lift modification. So let's save out that unmodified level data from Nebulus. So here we are back in Nebulus with an unmodified level. Let's save that data as a separate file so that when we compress it using this new compression code in Python, then the compressed output should match precisely, or near as much as precisely, as what we see in the game, assuming that the game doesn't do too much modification to the level as it's in memory, say for example if enemies are moving around or whatever it does after the initial decompression. So this default is the default level 1 data, hopefully the pristine copy of the level data. So going back to my debugging notes, the bit fields were at 2000 in hex, and the platform object type numbers were at 3018. So this data here should be practically almost, hopefully, identical to the compressed output data when I run the Python code. Oh yeah, I need to make sure that the memory is clear, and then let it decompress, and then I need to save that data out like last time, right? I need to make sure that the memory needs to be clear because the decompression is sparse. There we go, we've got nice initialized memory now. So even though the compression routine is sparse, the decompression routine is sparse. In other words, it doesn't initialize the whole memory range, it just initializes the level data for what it needs. So as long as I'm compressing the correct number of rows for the level, then it should be fine. So anyway, let's open the original unmodified level data file, and then let's run that through this compression routine. The compression routine is pretty simple Python code. I'm going to check that into source control as well, so you can have a look at it. And if you wanted to, you could take this code and then use it to insert your own levels back into Nebulus and then expand the game that way. So anyway, these are the bits and these are the tiles, in other words, the platform or object types. So the bit fields. So the bit field data has a 2-byte header for the memory address, because it's a PRG file, of course. And then it has 00FF4404. And that's not quite the same, I don't think, as the bit fields in my compressed output. I wonder why that is. Let's have a look at the code to see why. I've probably got a bug in there. Well, I found the bug. The current segment actually should be 0 and then 8. We don't need a current segment variable for that. This compress single bit field value has to compress 8 segments at a time. Now, if we have a look at the output bits, we've got 00FF074404, which is the bit field data, and the bit field data matches, I think, if I remember correctly, the bit field data that's in the memory. There we go, 00FF074404. So the start of the bit field data looks correct. Let's just double check the bytes, I think, at the end of the bit field data, and the bytes at the end of the bit field data by I, they also look correct. So since the bit field data is correct, that kind of like tells me now that at least the compression algorithm kind of matches, which is good, right? These end bytes for the bit fields look correct as well. 12, 0, 2, 1, 2, 12, 0, 2, and then followed by zeros. So we have this repeating pattern here. So the top of the tower seems to have the same rows in terms of which rows are being used. Maybe the tile bytes are not the same, but at least that seems to work. So let's compress the updated level now. So this updated level data, which was saved from the game, is basically the level data which contains the very long lift. Right, so the original data was fine. So let's just compress the lift data and then load that lift data, the compressed lift level with the extended lift data. Let's load that back into the game and see what the game decompression does when it decompresses that data. We should see the same, right? So this is the original level data, right? The original level data shows that it's all fine. So let's get that output file. Wow, I really can't type. Right, okay. So let's get the compressed output level file name, which is for the typo there. It's bits, not bits. There we go, because it's bit fields, not a single bit field, right? And then we want the tiled data, which is the platforms and objects data, and you can see the memory locations that it loads those to. Then let's go into the level and see what we see on the game, and there we go. We have compressed level data, which has been recompressed, and it contains that tall lift. So this is a good proof of concept, right, of updating the compressed level data in Nebulus and then getting Nebulus to render that modified compressed level data. So in theory, somebody could take this work and then use it to create a whole new series of levels for Nebulus. There's a little bit of work to do to understand the enemy placement, I think, perhaps. But that should not be too difficult, perhaps. But we'll see. Anyway, but at least, the towers can be modified, which is pretty cool in itself. If you wanted to produce a cheaty version of Nebulus, then you could just insert a great big tall lift into every single level and then just complete them that way. Right. That would be quite funny, but also a bit pointless. Especially since with emulation these days, it just makes it easier just to go into the emulation monitor and just enter the memory manipulation or a memory update, memory write command after the decompression routine is finished, and to do it that way you don't need to recompress the level data. But hey, it's an interesting thought experiment at the very least to understand the game's level data compression. So I'm just updating my debugging notes text file there. And now let's get set up for having a look at how the sprite mirroring works. So one of my watchers requested to have a look at this, so we're going to have a look at the sprite mirroring. So usefully, between levels and between the intermission screen and it displaying the tower level, the sprites in the middle of this sprite memory here, where you've got the Nebulus logo and stuff like that, and the little the spinning fish, those get dynamically updated to either be the mirrored versions of the player characters or the sprites used during this bonus level. So that's useful to know because we can have a look, we can find a good memory range by trying to clear the sprites to see if we can find a memory range which contains the memory for the sprite frames. Once we have a good memory range for the sprite frames, then we can put a watch breakpoint for memory stores to find out where the code does the right for restoring back the flipped sprite frames. We can see here that it's doing a load accumulate with 1200, x and then storing it into an indirected 04, and it's going to also be 05 for the low and high byte for the indirected addressing mode, y there. The indirected addressing mode is with those brackets at AD44. We can see that it's doing some repeated stores with altering the Y register, so it seems to be pulling original sprite data from 02 and then transferring that original sprite data to X and then indexing it with this 1200 table in memory. So look, the 1200 in hex memory lookup table is actually just multicolor sprite bit pairs being flipped over. And we have another routine at AD5D, which is loading it with 1300. So that's almost certainly going to be the high resolution version. So these bit pairs, if you've got, say for example, 1 in the bottom 2 bits, then you want 01 to be up in the highest 2 bits, and that's what that memory lookup table is doing there. It's just basically taking values and mirroring them in the X. So this sprite data mirroring routine is just basically lookup table driven, which is a really efficient way of doing it in terms of speed, but it uses, at least 256 extra bytes for multicolor data and another 256 bytes for the high resolution data. The high resolution data doesn't swap over or doesn't flip bit pairs, it just flips the bits, it swaps the bits, right? So you need to have 2 different lookup tables, so that's 512 bytes, 2 times 256 in total. For speed, it's better to do it that way. It would take quite a bit of code. If you wanted to make the code really small, you could have quite slow code, and it would take a more noticeable amount of time to flip that many sprites. But the code would be a lot smaller, but I guess if you wanted to have it for speed purposes, because it's a transition between, the intermission screen and back to the tower again, you probably want it to be relatively fast. You don't want to have an empty couple of frames for doing the slow code-based sprite mirroring. So there we go. It just uses a lookup table. So I think we can leave this video there. There's already quite a lot of content to put into this, and I need to edit it down and then release it. So if you like these kind of deep technical dive videos into old Commodore 64 retro games, then please do consider liking or subscribing to my channel. And I hope to see you around next time. I will of course check in this debugging text file, and I will check into source control the nebulus.py file, which does the data compression, so you can have a look at this yourself. And take care. Yes, thank you very much for watching.